I've got a puzzle for you today. Focus on this function which creates and populates a list of numbers. How does it compare to another function which returns numbers using yield_return? Specifically, I want you to compare them by speed. Which of these calls will turn out faster when I request 10 numbers? Will anything change if I ask for 10 million numbers? If you enjoy playing games, then you can pause the video and go straight to the comments to write down your expectations. Then come back and continue watching. So, the question is, which call is faster? But that question is wrong. It is wrong because the two calls do not do the same thing. The first call creates and then populates a list. The second call just instantiates a finite state machine acting as an enumerator. It populates nothing yet. I have seen people actually benchmark such calls and post shocking findings. That is wrong. The mistake I made here is that I forgot to iterate the IEnumerable during the experiment. Without enumerating the lazy evaluated sequence, nothing happens. Unfortunately, many people fail to grasp this concept. Hence this video, in which we will unveil the inner workings of yield_return and IEnumerable returns. $1 million question is, what on earth happens when I call this function and loop through the result? That is 2 questions, $500,000 each. To understand this, you need to know how foreach works first. Foreach is a shorthand syntax for a complete implementation of the iterator design pattern consumer. It first obtains the enumerable object. In this example, that is the result of calling the function. If you remember my first question about comparing performance, this was all I did there. Now you see why I said that such a call didn't populate any numbers. The remaining work was missing. The foreach loop would then obtain the iterator itself, which .NET calls the enumerator. The enumerator lets us visit each element of the sequence in turn. It does so in the moveNext method, which returns true after it successfully stepped to the next element and false if there were no more elements. Therefore, the foreach loop is just a while loop in disguise. Inside the loop, you can safely access the current element of the sequence and do with it whatever you plan to do. I will now show you how this expanded foreach loop relates to the function below. Getting the enumerator does nothing but initialize the enumerator's internal counter to 0. A call to move next is essentially a test of whether the number is less than n. Any subsequent call to move next would involve incrementing the counter before comparing it to n. And accessing the current property is literally what the yield_return instruction is giving us, the current value of the counter. This is the complete story of foreach loops. There is really not much to tell about them. That leaves us with the producing side, this loop with the yield_return in it. How does that work? It is an example of compiler magic, but, lucky for us, a simple kind of magic. The function returns an object implementing the generic IEnumerable interface. What class is that object? There is no such class readily available, so the compiler will get its hands dirty and generate one. There will be a class created secretly by the compiler, and that class will implement the generic IEnumerable interface. All the IEnumerable does is produce the IEnumerator object, which isolates individual iterations over the same collection. That is the .NET implementation of the iterator design pattern. Therefore, the compiler will also generate the enumerator class. The enumerable will simply return a fresh instance, ensuring that each iteration over the numbers is isolated from any other. That is another miracle you get for granted with foreach loops. You can nest loops and they will not affect one another, thanks to operating on separate instances of the enumerator. Now you know that too. Tap yourself on the shoulder. The enumerator itself must implement a couple of members. The 3 members that count are moveNext, current, and reset. The moveNext method advances the enumerator and returns a Boolean result indicating whether it succeeded or not. The current property would return the current element provided that moveNext had been called before and returned true. You may throw if there was no successful call to move next before accessing current. The reset method returns the enumerator to the beginning if possible. You may throw if your enumerator doesn't support resetting. That is the proposition. We are now left with this loop and the question of how to translate it into the enumerator class below. Let me unwind this loop so that you can see a glimpse of that future finite state machine I mentioned, which the compiler will generate. At the outset, it is only a counter initialized to 0 along with the state declaration. Then comes the analysis. In the initial state, we only check the bound and either advance to state number 1 or to the terminal state 2. In state number 1, we increment the counter and then repeat the analysis. State 2 is the terminal state. You will notice that each yield instruction terminates one call to move next. Yield return makes move next return true, and yield break makes it return false. This screen displays all the magic the compiler will apply when you write a method with yield return. It is just a systematic, formal transformation of the original code. I will now show you how you can write a custom enumerator that does this, should you ever need to. Before that, let me mention my Patreon page. This channel is free thanks to the patrons. If you enjoyed watching this video, then please consider joining the growing community of supporters on Patreon. Every patron helps hundreds of other fellow programmers watch all the videos on my YouTube channel for free. You will find the links in the description. Let's implement this class now. There are 3 pieces of state here: the parameter n, the counter, and the state variable itself. The parameter will come from the outside. The enumerator object manages the rest. Move next is the central method. Finite state machines may look scary, but they are straightforward in fact. Every iteration produces a new state. All you need to do is calculate the progression meticulously. Make sure to avoid making mistakes and you'll be fine. This finite state machine is correct, or at least I should hope so. The reset method is trivial. It brings the object to the state in which it was upon creation. What you see here is one possible implementation of a class that corresponds to the loop with yield return. Here is that loop again. If you have ever wondered what happens behind the scenes when you write code like this, here you have seen what happens. You will use yield return liberally in your designs. There's no reason not to. A foreach loop would consume the enumerator and use the enumerated values. There's no functional difference between that and the use of an explicit enumerator object. Both loops will print the same sequence of numbers. The difference is in how much code you write. Any method that can utilize yield return and yield break will be way shorter than any alternative conceivable.